There we go, number 4. So we're going to determine the voltage V1 using KVL, Kirchhoff's voltage law, right? That says what goes up must come down, or the sum in a closed loop will go to 0. I'm going to just do the sum of the loop equals to 0, the sum of the voltages in a loop equaling 0, which means that I need to consider the rises and the drops, or the way that I'm going at it. I can pick either direction as a loop. I'm going to pick this way because that's just typically, I just always draw my loops in a clockwise direction initially and find that to be the easiest. So if I'm ticking up, first thing I hit is a rise, right? From negative to positive. So I'm putting all my rises and drops, and I'm going to put 0 on one side. This one's positive 16 because I went up from the low side to the high side. So I'm writing my rises as positives, then it keeps going. And then I encounter a resistor. Well, I know this one's going to be a drop because I'm following this direction. So that is V1. That's my unknown. Danny, I think you're unmuted. And then it keeps following. Here's another resistor, minus 4.2 volts. And then here's the one spot where it may seem tricky, is that I encounter this 9-volt battery. And so this battery is a drop because I'm going in the direction of my loop from the high side to the low side. Notice how it matches the resistor from the high side to the low side. So it becomes minus 9 volts, right? So that's what we were discussing before in a concept check. And so my V1 comes out to 2.8 volts. If you need me to do the math to rearrange that, let me know.
Sir,
I think everyone's pretty comfortable with rearranging for a positive V1, pulling it to the other side, 16 minus 4.2 minus 9.
So there's another way you could think about it. So you're starting in that right above the battery or the ground in the bottom left there. And as you travel up, whatever side you end up on is the side or is the sign of the value, I guess, in the KVL equation. So for example, you're going across that from the negative.
So you're
to
saying
the positive,
because you go from whichever side you end on
is the sign of the value.
Is the sign of your loop. Yep. That's
Okay.
a way to do it. And mathematically, here's the thing. It works the other way too. If I wrote the mathematical equation in the other way now,
if you did everything
and
opposite.
if I did negative 16 plus V1 plus 4.2 plus 9, and all that equals 0, mathematically, V1 still comes out to 2.8 volts.
Got
And
it.
that's
Thank
kind
you,
of the point here, is that these laws, they work mathematically both ways. And you could do it with the rise and the drops. And I put my 16 on one side, and I put 4.2, 9, and V1 on the other. But just notice the main one is to see that 16 and 9 are opposing each other. So one is a battery the 9 is a battery receiving a charge. But yes, you're right, Ethan. That's a perfectly fine way to do it too. As far as if you just want to pick a rule. So if you wanted to pick a rule and just say, I'm going to always follow, what comes after, it goes through it, that works. Just be consistent.
Mm-hmm.
Yep. All right, number 10. That's number 9. There's number 10. So this one is you're first asked to redraw the circuit, and this is kind of like the example that was given in the video. But what I'm going to do first before I begin solving it with all of it is just notice my positive sides of my battery. Now, they are already given, right? And so I don't have to label it, but I find it helpful whenever I'm going to look at which ones are facing the same direction. Right? So if I pick my loop, or if I pick my rises, I'll do the rises and the drops on this one, or just all my voltage sources. We'll just say the sum of the voltage sources, because all of the series elements can be rearranged is what we're doing here, is we're interchanging, and they can be rearranged mathematically. In the real circuit, like if this was on a ship, this is actually where the battery sits and where the resistor sits. But when I'm just solving for an unknown value, I'm now doing equivalencies, which is what we'll be doing a lot, which is why I'll say redraw the circuit. It's helpful for you. So if we're redrawing this circuit, I just need to be consistent. So let's add up all of our voltage sources, right? And actually, I'll just put it as an E because E always means the sources. So the sum of my E's, if I'm starting from here and I'm going to go a loop around here, the way that I just did on the last problem is how I'll be consistent. So I'm going up through 12, I'm going up through 3, and then notice this arrow is going this direction, and I'm going down through 6. So the sum of all my E's, right, 12 plus 3 is 15, minus 6, 9 volts. And then my R total, I can add up these series elements. So even though this resistor, 27 kilo ohms, isn't directly in series, whenever I say series elements exclusively share one node, well, 27 and 33 don't exclusively share one node between them, but they are in series because then the 3 volt also is in series with 33, right? Or stated another way, the same current flows throughout them. So I can just add all of these up. 27 plus 33 plus 18 gives me 78 kilo ohms. So the one thing that you're going to want to do is make sure that you draw it in the correct direction, which, because the 12 was what we treated as positive and we ended with a positive 9, I need to match the direction of the 12. And I come around, here's my redrawn, 9 volts, 78 kilo ohms. And if I'm finding my I total, well, V equals IR is our favorite law. And I said subscripts, being consistent with it will help you make sure you grab the right ones, right? So I'm looking at V total equals I total, R total. V total over R total, 9 volts over 78 kilo ohms. And I total comes out to 115.4 microamps. That is micro, and I can point out on the calculator, but I recommend the way that I have it, and I'll pause the share real quick so that if I pause the share, I don't want to stop share. Or if I pause the share, I think it's highlighted on the video now, I'm assuming. But you can see here, I did the fraction button, 9, and then I use the fraction button that's right there above the 7. See the fraction button above the 7? Right, so I did 9 fraction button, 78 E3. E3 means kilo. And by doing that, it then spits it out to 0.000115. If you want to do the little, hopping across and count 6 over, I still will do that sometimes. With this one, it's pretty easy to recognize that I have 3 zeros. That takes me to milli. Go another 3, takes me to 115 micro. Another way to do it, if you're still uncomfortable with the notation, is hit mode on your calculator. And if I scroll across to where it says engineering and see where it's flashing, it will actually always put it in the engineering notation. And so if I type in that number and hit enter, now it did it 115 E -6, which means micro. So as long as you have those memorized, that's a tip on with a calculator. And I only need your final answer in engineering notation. Along the way, if you want to write decimals, that's fine, but it can get kind of messy if you're starting to write 0.000 whenever you're doing intermediate steps. And the way that I solve it is I always just pull my answer from my calculator back into my next problem. I don't type in 28.4 if I had a long set of digits. I'll just hit enter on that answer and pull it down into the calculator. Last one is 14. So we determine the voltage A, B in the circuit. Probably helpful to make sure we know what A is. Here's A, here's B. So that's this point right here. And what I'm looking across is I'm looking at R2. So in my voltage divider rule, that will become my Rx. I'm finding a VAB, so the voltage divider rule says that Vx equals V equivalent Rx R equivalent. So the Vx that I'm looking for is from A to B. VAB. The VEQ in this case happens to be the V total, because whenever I'm looking at series elements, all 3 of these are in series. Well, what is the total voltage across all of those? Well, it's right here, 110 volts. The Rx that I'm looking for is from R from A to B. Notice how I plugged in AB where the X was. And for EQ, I plugged in T and T. The X's have to be the same two nodes that you're picking from every time. And, or if it was just labeled R2, then the V, I could also label that as V2 if I had R2, or right there, right? Just be consistent with your subscripts and you'll make less mistakes. So VAB here, the V total, 110 volts. RAB, which I also said is RX, it's also R2. You choose whatever you see, whenever I'm saying these, you're like, yeah, that one makes sense to me, then just use that one and be consistent with it. If you're picking from one node to another or R2, right? Then I have 30. Well, then I need the series elements. Remember I said VDR is for series elements. Well, the three that are in series are 50 plus 30 plus 20. And VAB comes out to 33 volts. And if I'm typing that in on my calculator, I'm typing that all at once. I'm not typing each individual part. I find it easiest to just plug it in one fell swoop. If you want to solve it in parts on your calculator, you can. For me, that results in possibly more mistakes. And what I do like to do is make what I see in my calculator exactly like what I wrote it on the page. It results in less mistakes. So I'll pause the share again. And there is 110 parentheses 30 over 50 plus 30 plus 20 parentheses. I still have it in engineering notation, so it says 33E0, which means 33 volts. That was a longer explanation, but I think it was worth it. So that's the end of the